What team are you guys?
Hopping Blue Elephants, number 16480.
And how did you come up with those, what is the significance of your team name? And how did you come up with those elephant hats?
We wanted to find a quirky combination of words, so we used a word generator online, and we got hopping and blue, and then we focused on elephants because they're really intelligent animals, so we just put them together and we got hopping blue elephants, and we found these hats online.
Also because no one has ever seen a hopping elephant before, but we have. It is a secret.
About your chassis, why did you choose this particular design for it?
Okay, the reason our chassis is built the way it is to be as compact as possible so that it's easy to turn during the dog trainer mission, so it can roll over the dog and make it sit, and also so that the center of balance is really forward, so when it can climb the wall because it's in front of the triangle that supports the wall.
So what are the pros and cons of your design? What are the pros and cons of your chassis?
Okay, so we made the motors, the driving motors, upright so that it can be like closer together. But the problem with this is that sometimes if it stops too suddenly, then it actually tilts forward and it like hits the front of the robot against the ground, which can mess up the program sometimes. And the pros is that it's really small, so it can fit in tight spaces.
So how did you account for your design problem, and what did you do?
Okay, so we have a slow down program so that it won't stop as suddenly, and we have a PID program to keep it on track, which Michael's gonna,
Or do you have any programs for individual missions and group missions? Like, did you group some missions up?
Well, the actual way we organize the programs is we put it in a master program, which you can run a specific program by pressing a certain sequence of buttons. And this is to allow us greater versatility in choosing which missions we want to run. So for example, if we're running out of time on one mission, we don't feel it's important enough and that we need to skip over it, we can just skip over it. And so that way we're not forced to follow a certain sequence of missions.
We also saw that on the mat, like certain missions were really close together, so it would be easier to do them together.
How have your attachments evolved over time? Because obviously at the beginning.
Can you also show us all your attachments?
Okay, so for Kaylee's and I's attachments, we use these things called C-clips. They're sort of like brackets, so once the robot hits one side of the bracket, the other side automatically clips down to the bottom of the robot, so it's really stable and it's easy. And it's really easy to take off the robot as well.
Yeah, and this has evolved from the regular peg in which you stick into the robot, because sometimes when you pull your attachment off, then the pegs get stuck in there and you can't pull them out.
Cool.
Can you also show me what each one of these do? What each one of these do?
Okay, so that's for getting food. This is the climb wall. That's the bunch of missions in the corner.
This is for dispensing food, and this is for scooping up things in the wall following on the left side.
Cool.
So I'm going to demonstrate how quick you put this into the robot. So I can just stick these axles in here and I can lock this so it won't shake around.
So it moves really quickly.
Which sensors do you use to ensure accuracy for your robot? Can you show them to us?
So we would use the gyro sensor, which is in here, I think. Wait, there's the gyro sensor.
Gyro sensor is that one.
No,
It's
no.
this one.
Oh, it's
yeah, this one.
Okay, the gyro sensor is right here, and it allows us to see what degree measure the robot's facing. So that way we can always stay at a certain angle. For example, if we want the robot to go straight, then it can just stay straight using the PID program. And the way that would look would be like if you were to run it, I don't know if your cameras can see this, but and you knock it off course, it would recover back. And we use that using the gyro sensor, and we use the light sensors to detect lines and follow them. And we use twos because 2 points form a line, so we can square up with lines.
What mission was the hardest one to get working?
Probably the cow and getting the milk, only because it's really hard to sort of aim at a particular spot and then see if you can follow the line.
When you got to the tournament, which missions didn't work? How did you fix them?
The cow and basically what we just talked about. We fixed it by changing our angle of approach to the circle, which we can follow the line. And during our last run here, which we just finished, we actually managed to get it to work. Yay!
When you went home from the qualifier, did the tweaks you made at the qualifier work on your home mat?
No, not really.
So what did you do in that case?
Well, we also changed the robot after the qualifier round, so in a way, we sort of had to reprogram everything.
So what's the best score you can possibly get?
190.
In theory or in reality?
In theory.
In
Supposing everything works.
Supposing everything works, 190.
So how do you guys split responsibilities?
Well, we usually do things as a team, and like for our meetings, we would, let's say we would have a meeting on Saturday that would mainly focus on robotics, and on Sunday we would have a meeting that mainly focuses on project.
Did you build more than one robot?
Yes.
Yes,
How many?
like 4, 5-ish.
And how did you deal with the inconsistencies between robots?
Reprogram.
Reprogramming.
So how often did you guys meet during the season?
Twice a week.
Twice a week, Saturday and Sunday, which
Sometimes during the weekdays, if we wanted to work on our particular mission.
How long have each of you been in FLL?
this is my first year.
This is my second year.
Second,
Second.
How did you come into FLL?
we invited him.
Yeah, the coach for this team knew me. She's like, hey, do you want to go join our team? We do cool Lego stuff like FLL. I was like, okay.
So you brought your laptop. Did you want to do something with that?
So this is one thing that we always use. It's called PID. It utilizes elements of calculus like integrals and derivatives. And what it is it's the program that you saw that allows the robot to go straight. So you take the error, how much you're off from where you want to be, like in terms of the gyro, and you multiply that by the constant of p of the proportionality, and then you keep continuously add the error through every loop, so you can get the integral, so that the robot can correct for steady state error. Like let's say the robot is always tilted towards the left, then the robot will eventually realize the errors always happen on the left, therefore it must drive more to the right. And then we use a derivative to calculate the rate of change to see how fast the errors are adding up. We multiply all these together, and we get a turn value, and yeah, and it just repeats the loop every 0.0028 seconds. And we can end the loop using any sort of exit condition. For example, when the robot sees a certain line, when it scares up with a line, when it's gone a certain number of degrees on the motor, or when it reaches a certain gyro angle. And we have the exact same version of this but written for light sensor, so that we can follow lines very quickly as well.